Hello everyone, this is chapter 4.1 where we'll be discussing maximum and minimum values of a function. And so I have a lot written here, of course, and a lot of it's really kind of in technical math lingo. I'll say it out loud, but then I'm going to just give you kind of an intuitive idea of what it is with the visualization, which I think is kind of more important in my opinion. But here we let C be a number in the domain of F. I'm calling the domain D just for short, so I don't write too much. Then f of c is an absolute max if f of c is bigger than or equal to f of x for all x in the domain D, and absolute minimum if f of c is smaller than f of x for all x in the domain D. So in other words, f of c is the largest of all of the values, and f of c is the smallest of all of the values. Now remember, f of x values will be the y values. So really what I'm saying is that either it's the highest y value in the region or the smallest in the region. And the region being just the domain of f. Now here, local max and min similarly are the exact same. So maximum is where f of c is larger than f of x, minimum is where f of c is smaller than f of x. Only here, instead of it being for all x in the domain D, we're letting x be just some number that's near c. So hence the word local. So it's not maybe the largest for all values, if it's maximum, for instance, but it'll be the largest in a small kind of open region, basically. So here's the visualization that'll hopefully give us an intuition. So let's imagine we have this x-axis, and I guess just so we can kind of compare more easily, let's say we have this y-axis. Let me just make it straight, that looks okay. And I'm just going to draw some curve like this. So this curve, let's say, is f of x. And in red, let me just draw the points which are the highs and lows. So I have this point, this point, this point, and I guess this point. And also just to be a little more clear, let me make it a section of a graph. That way there's no, well, I'm not making it go on indefinitely. We could if you want to look at those cases, but in this case I think this next idea will become a little more clear in this case. So what I'm going to do now is I'm going to point at points that are the maximums and minimums. So this is a high point, so this is a max. This is a low point, so this is a minimum. This is another low point, so this is also a minimum. And these points are actually maximums because they're the largest in their own region. So this point and this point is what I was referring to. So even though there's nothing to the right and here there's nothing to the left of those points, they're still the largest of values near them. So now, of course, the absolute max is the largest of the maximums, which would be this guy. So this is technically absolute, whereas these will just be then local. So I hope that's pretty clear. Similarly for these, well, the smallest of the minimums would be the absolute minimum. That's going to be this one, whereas this one here is minimum in its own small region, but it's not minimum overall, so this will be only local, not absolute. So even though this is a section of a graph, if you just imagine this section of x values is the domain of f, then it's really just that idea. And the only issue is that we have these endpoints, and if you have a graph that goes on, there are no endpoints. So just to be a little more clear and to give you some other visualization, let's imagine we have some weird curve like this. Here, there's only one maximum, and it's absolute. There is no minimum in this case because there's no lowest value that we attain here, which is kind of funny. So here there's a horizontal asymptote at the x-axis, so it gets smaller and smaller and closer. So no matter what point you want to say is the minimum, so it'll have the smallest y value, there exists one that's even smaller because it'll get closer and closer to the x-axis and never touch it. So it's kind of weird to think about, but there do exist cases like that. In fact, just to show you another one, and let's, by the way, just say the y-axis is here, and just to show you another bizarre scenario, this one I can actually give you a specific function. So if you take a look at this is the graph of, let's say, y equals x cubed. This is actually an example of, it's a weird example, but it's an example nonetheless of a case where we actually have no max or mins. we have this kind of swivel point, which we'll discuss in a later section, but there's no high and there's no low, so there's no max and min actually. Not even local or absolute, just none. Here there's only one and it's absolute. Now, when talking about absolute and local, notice everything is local. Meaning if you have a maximum or minimum, if you don't worry about absolute, you're only talking about being max or min in its own region. And in fact, that's the first thing I looked at, the highs and lows in their own region. Then beyond that, I looked for the highest of the highs is absolute max, the lowest of the lows is absolute min. So in reality, all maximums or mins are local. So if it's absolute, then it's local. But if it's local, it doesn't necessarily mean it's absolute. So it's something to kind of keep in mind. Okay, now the other thing though is that these are weird scenarios we get where we possibly have no max or min. It is also possible that you have local only and no absolute. So kind of think of something similar to this. What if we had something where we had local max and mins, here's a local max and here's a local min, but there's no absolute max or min because there are points that are lower than any low point you pick and high points that are higher than any high point you pick. So there's actually no absolute max and no absolute min. Okay. Now, as it turns out, if we are on a closed interval, there has to be an absolute max and there has to be an absolute min. And that's exactly what the extreme value theorem here says, that you've probably been eyeing at the whole time. So I'm calling this EVT for short, and EVT says if f is a continuous function on the interval a to b, then f attains an absolute max and absolute min on this interval. Now, to be continuous, you have to make sure that, continuous basically means there's no discontinuities. And in fact, the reason why we need that is because let's say there was a vertical asymptote somewhere in between a closed interval, then the function could do something like this, and there'd be no highest high and no lowest low, because it would go on and on and on. So there's no point that would legitimately be the absolute max or the absolute min. But if you don't have a scenario where you have a discontinuity or even a vertical asymptote, then you have scenarios like this. These scenarios can never happen. Why? Because if you were to look at a closed interval, because all of these are so far with the arrows anyways, are from negative infinity to infinity, which is open if you think about it. So if you consider this on a closed interval, then this actually gets cut off and now becomes a section like this. Now this actually had an absolute max, so that was already good, but it had no absolute mins, now it does. It so happens they're a tie depending where you end things at, but that's possible. It's possible you have two absolute maxes or two absolute minimums. You could have multiple of them actually. But it's weird because if you look at the wording here, f of c is a absolute max or absolute min. F of c is a y value. So you could have two different locations for an absolute minimum in this case, but you'll still have only one absolute minimum. So for instance, let's say these both correspond to the same y value. That y value would be our absolute minimum. It would occur at two different x values, but the actual value isn't a point, it's the y value. So that's something to keep in mind. And similarly here, if we cut this off on a closed interval, then that sections this off like this. And now, before we didn't have absolute max or absolute min, but now we do. Perfect. And that's basically all I wanted to say about the extreme value theorem. One thing I should also say is the reason why it's called extreme value is because the word extrema means max or min. So absolute extrema would be an absolute max or min. Local extrema would be a local max or a local min. So max and mins are just specific cases of extrema. Anyways, with that being said, now we're going to actually see how calculus plays a role in this. And in fact, I'll just kind of mention it right now. Notice at any point where we have continuity on both sides, let's say like this point, this hump right here, That's where we have a local max actually. If you consider a tangent line at this point, what do you notice about the tangent line? Same can be said about any of these points where, again, it's continuous on both sides, so not the endpoints basically. Or similarly here, what do you notice about these tangent lines? What do they have in common? So we'll take a look at that right now, and well, there's a few other ideas in 4.1, but this next idea is kind of the key that connects calculus to finding extrema. Right, so if you try to figure out what I was trying to talk about as far as what those things had in common, of course, it was that all the tangent lines were horizontal. And what does it mean for a line to be horizontal as far as slope goes? Horizontal lines have slope 0. So that means that the derivative, which is the slope of the tangent line, of course, would then be 0. And that's exactly what this says for Fermat's theorem. And it says if f has a local extrema at x equals c, and if f prime of c exists, we'll talk about that in a second, then f prime of c must be 0. So really what it's saying is that if you have a function like this, it's a smooth function, and let's say there's an x value c where there is a local max or local min, in this case it's a local max, then it must be the case that there is a horizontal tangent line. In other words, f prime of c, the slope of this line, is indeed 0. Now, I said smooth, meaning that its derivatives exist. In order for something to be smooth, there's basically no sharp edges. So in actuality, this is kind of like a perfect scenario. But in actuality, you could have scenarios that are kind of rare, but we'll see them. We'll actually see an example of one kind of like this. We actually will have cases like this. It's possible. So your function could look, let's say, like this. Now, what's bad about this, obviously it's not smooth, there's a sharp point. Now, what that sharp point basically means is that there is a point, at this particular point that is, where we have a vertical tangent line. So in fact, if you try to look at tangent lines here, so this is indeed a maximum. So here, the tangent line is horizontal, here the tangent line is horizontal, here the tangent line is horizontal. And if you look at what the tangent line is doing for each of these points, you'll see it's getting steeper and steeper and steeper until it gets up here, and then it'll get less steep until it finally settles at 0. So at this point, we actually have a vertical tangent line. And what's bad about vertical lines is, well, if you remember, similar to horizontal lines again have a slope of 0. Here, a vertical tangent line, well, any vertical line that is, has a slope of, well, undefined. Meaning its derivative doesn't exist at that point. So that's what I was saying. If it's smooth, there are no sharp edges, in which case no vertical tangent line happens, and the vertical tangent lines would only happen when the derivative doesn't exist, so that means it would be smooth if the derivative exists everywhere. So that's what this is basically saying. So to generalize Fermat's theorem, if f has a local extrema at c, and we don't have this part of f prime existing, then either f prime of c would be 0 or undefined. So these are the kind of the only places you really have a max or min where the slope is 0 or undefined. There are some other scenarios, and I guess those would have to be endpoints, why I kind of pause for a moment. So if you take a look at something where we look at it at a closed interval, which I actually look at in a second, we'll have these endpoints, and continuity at a particular endpoint, at a closed point, is kind of hard to discuss. So for that reason, really you want to consider all endpoints. So I guess that would be the other issue, would be endpoints. But by the way, where the slope is 0 and where the derivative is 0 and where the derivative doesn't exist is something we'll be taking a look at even further into more detail after this example. So let's take a look at this example now. So here I ask, find all extrema for f of x equals this on this interval. So I want to find all max and mins, and I'm going to actually categorize them by local or absolute. So the first thing I'm going to do is I'm going to take advantage of Fermat's theorem, And I'm going to say that since this function has a derivative that always exists because there's no zero denominators basically, in fact, I'll show you what it is. Its derivative is what? It's 6x squared, that should be a square, minus 30x plus 36. So since the derivative here is a polynomial basically, its domain is negative infinity to infinity, its derivative exists everywhere, so that means Fermat's theorem is applicable, meaning a local extrema of f of x would be where f prime of x would be equal to 0. So now what I want to do is I want to set this equal to 0, solve for x. Okay, cool. So to set this equal to 0 and solve for x, I want to factor the non-zero side. So I'm going to pull out 6, and we'll get this. And notice this can be factored further as, I guess, x minus 3 times x minus 2. Perfect. And then by the zero factor property, basically, well, notice 6 is never 0, so we can ignore that. You can just divide by 6 because it's non-zero. Here, if this is 0, then that means x is equal to 3. And if this is 0, that means x is equal to 2. Cool. So we have these 2 points where a max or min possibly occurs. It doesn't mean that they have to be max or mins. It's just where they can possibly occur. Because remember, the wording is very specific in Fermat's theorem. It says, if it has a local extrema at these points and its derivative exists, then its derivative must be 0. We don't know if a max or min is at these points. We just know these are possible x values where a max or min can occur. So now what I'm going to do is I'm going to plug these in to see, well, what the actual values are. Also, I haven't yet considered on this interval, because the problem said on this interval, closed interval. So what I'm going to now consider basically is the extreme value theorem, EVT, which says that absolute max or min always exists. But you have to consider the endpoints. So here I'm going to plug in the endpoints as well as plug in these numbers. So let's see what happens. So I want to find f of 0, f of 2, f of 3, and f of 5. Now it's going to take a little bit of work, so I'm going to pause this and I'm going to just write down the numbers here, but I'll leave it to you on your own to verify that these are indeed correct. All right, so these are the values I got, negative 12, 16, 15, and 45. And the largest of all of these is, of course, this one. So this will correspond to our absolute max. So we have an absolute max being 43, and it occurs at x value 5. Perfect. Now, the smallest one would then be this, negative 12, so that means the absolute minimum would then be negative 12, and that occurs at x equals, well, 0. So I'll box these. Now you may ask, what about the other ones? So as it turns out, the other ones are indeed max and mins, and they are local. Now, as far as how we can efficiently determine that, we're going to have to kind of save that for a different time. In fact, 4.3 really is where we start to see more machinery, I guess you can say, as far as figuring that part out. Otherwise, you'd have to plug in numbers around 3 and 2 into f and see if they'll be higher or lower than this. Now, as it turns out, it'll kind of give us some intuition, and you can also graph to compare. So if you take a look at the interval 0 to 5, like this, we wanted to consider the values in between 2 and 3. So let me just try to make this kind of spaced out. So let's say 2 and 3 right here. Now we know when we plug in 0, we get negative 12, so the y value will be negative 12. Let's say that's down here. And we know when we plug in 2 and 3, we get those values. So 2 will give us 16. 3 is going to be a little lower, so it's going to be at 15. And for 5, we get 43. Perfect. Now the graph actually extends beyond this in general, but on the closed interval 0 to 5, this is the only window we see as far as x and y values go. And in fact, the image actually is this, if you connect the dots. Now the reason why I kept kind of holding off on saying that at 2 and 3 there may not be a max or min is because in general there are cases where this kind of fakes us out, where the derivative is 0 but that value actually isn't a max or a min. There are higher or lower values that surround those. And that basically has to do with the fact that when you would plug that number into the second derivative, it would also be 0. But again, we'll have to discuss that more in detail in a later video for 4.3. But for right now, you can compare with the graph, and this is indeed going to be the image you'll get, meaning that at 2, we would have a local max. So I'm just going to say 16 is a local max. And of course, that occurs at x equals 2. So if you want to write it in that way, you can, but I'm just out of space, so I'll just write this is our local max. I guess I'll circle that. And of course, 3 would then be our local minimum. So let me write local minimum here. Okay, good. All right, so now what I explained earlier as far as this number c goes, I said that, well, f prime of c would be 0, but I also said it's possible f prime of c could be undefined. So now we're going to define what that value c is. It's called a critical number, and in fact we can use it to generalize this idea to try to better find extrema for a function. Right, so here I say a critical number c is a number in the domain of a function f such that either f prime of c is 0 or f prime of c is undefined or does not exist. Kind of like I've been hyping up from the previous screen. So now what we're going to do is we're going to find all critical numbers for a particular function, and then beyond this I'll discuss how that affects its extremas. So let's take a look. What we want to do is we want to find the derivative first and then see where it's either equal to 0 or undefined. And what that basically amounts to is writing the derivative as a function, or as a fraction I should say, setting the top equal to 0, meaning the whole fraction is 0, or setting the bottom equal to 0, meaning it would be undefined. Now in this case we can do that. Notice the domain of f here is all real numbers, because even though it has a fraction power, the denominator is odd, meaning it's an odd root, and that accepts negatives in the domain. Oh, in the, so you can plug in a negative for x basically. So there's no issue with the domain there. Anyways, what I really want to do here is I want to distribute. Otherwise, you'd have to use the product rule to find the derivative, and why do the product rule if you can avoid it? So f of x in this case is going to be 4x to the 3/2 minus x to the 8, I meant to say 3 over 5, minus x to the 8 over 5, because of course if you add 1 to 3 over 5, you get 8 over 5. And then from here, if we find the derivative, f prime of x, we get, let's see, 12 over 5, x to the 3 over 5 minus 1 is negative 2 over 5, minus 8 over 5, x to the, let's see, 8 over 5 minus 1 is just back to 3/5. Perfect. And if we want to write this as one fraction, there are a few ways of doing it. The best way I know is to, well, first bring this in the denominator and then find a common denominator. So we can actually write this as 12 over 5x to the 2/5 minus 8x to the 3/5 over 5. So we need to multiply top and bottom of the second fraction here by x to the 2/5. And that's actually quite nice, because when we do that, we get no fraction powers on the top now, because notice 3/5 plus 2/5 in the power is just 5/5, which is 1. So we end up getting 12 minus 8x to the 1, which is just 8x, over 5x to the 2/5. Perfect. So that is the derivative, and we want to find out when this is 0 and when it is undefined. Now again, a fraction is 0 when the numerator is 0. So I really want to set the top equal to 0 and the bottom equal to 0 to see where the derivative doesn't exist. So now the top one, let me just write it over here to use this side of the board. This is pretty easy. If you add 8x to the other side, you get 12 is equal to 8x, divide by 8. Then you get x is equal to, you can divide by 4, you get 3 over 2, or 1.5. But that's fine. So this is one of our critical numbers. Great. Now our other critical number is when the bottom is equal to 0. And notice when 5x to the 2/5 is equal to 0, dividing by 5 will give us x to that power is 0, which would imply that x is 0 actually. So we actually get these two as our critical numbers. But here, this is where f prime was. So I'm calling them x, but really they're what we call c. So let me just say this is where f prime of x is equal to 0, and this is where f prime of x doesn't exist. Which is good to keep in mind, because if you consider the graph, which I'll allow you to graph on your own, but I'll at least draw it here. So I'm not going to justify how I'm getting this image, but you can graph it on your own and you'll see you'll indeed get the following image. You'll get something like this, and in fact it doesn't taper off, it just kind of continues to go back down. Let me try to do that a little more smoothly. That's kind of better. But now the big point here that I want to emphasize on is at 0, there, notice, is a vertical tangent line. It's not a max or min though. It's possible it could have been a max or min, but it so happens it's not, which I kind of warned you of previously. Now here, let's just say this is the x value 3/2, which we know is the other critical number, is where f prime of x is 0, which indeed actually corresponds to a horizontal tangent line, and moreover, it's actually a maximum. In fact, it's the absolute maximum of the function. So this function actually has no minimums, local or absolute, but it does have a maximum. In fact, it has an absolute maximum. So I didn't show how we can find those max or mins without graphing, but it just so happens that when you graph, you actually get this. But again, in 4.3, we're going to develop a lot more technology, so to speak, that will allow us to actually uncover the mystery behind when something is or is not local or just an extrema in general. Right now, it's kind of hard to say just because we don't have too much of those details panned out. But at least what we can say is these are critical numbers, and this is how critical numbers affect, essentially, the graph of a function, or at least how they play a role. Well, in any event, that was it for 4.1. That's all I want to say about that. Thanks for watching. I'll see you in the next videos for the rest of Chapter 4. It's going to be a lot of fun. See you then.